Let me start from where we arrived at last time. In particular, a result that we obtained is the following. So the operator EI of S, where S represents a certain surface. Now, I will remind you what this surface is. This operator EI that we call EI is acting on H sub gamma of S overlined S underlined, and this is equal to 8 pi beta G H sub gamma 1 S overlined S. Then we have tau I, and then we have H sub gamma 2 S S underlined, and we considered a surface that we called S, and then we had a curve gamma that intersected this surface at a certain point S, lowercase s, and then here we have the curve gamma coming out of the surface. And the portion that's going towards the surface, we called it gamma 2, and the portion that's moving out of the surface, we called it gamma 1. So you can see that there is only just one point of intersection between the surface and the curve. Then we also derived another important result, which is the following. So we acted with E sub I of S, the surface S. Then we have another E sub I of S. And now I'm assuming that I'm summing over I because this index here is repeated. So you have to sum over I. And then we act with, we act with EI on H sub gamma, the holonomy, S overlined, S underlined, and what we derived is the following result. We found 8 pi G beta squared, and then we have 1 half plus 1. So we wrote this in this fashion instead of summing 1 half with 1, because this is reminiscent of the eigenvalues of Li in particular. So in quantum mechanics, this is L1 squared plus L2 squared plus L3 squared, which is often just denoted as L squared. So it's angular momentum squared. And the eigenvalues of angular momentum squared, when we consider spin equal to 1 half, are exactly like this. Or in general, they are written in the form j times j plus 1, where j is the spin. In this case, we have 1 half. We'll get back to that. And then here on the right, we still have the holonomy H sub gamma of S overlined, S underlined, like this. Now, as a further generalization, we consider a curve, and we still call the curve gamma. But in this case, let me sketch something a little bit more complicated. It's not too complicated conceptually, but just let me do it. So here I have a surface that we can still call S, and then we also have a curve gamma. The curve gamma intersects the surface at a certain point. For example, let's call this point K. So this might be PK or whatever point you want. So you can label it the way you want. Now let me not. So let me avoid labeling this point. And then the curve gamma is protruding from the surface, so it's moving out of the surface, and then it will move down again, and it will intersect the surface again at another point, and then it will move underside of the surface, and it will go back up, and it will intersect at another point. So this is just a generalization of what we had above, where in this case we have 3 points. So for example, we can label this P1, P2, and P3, And we can consider, for example, this small element, surface element, we can call this S sub 2. This small surface element, this will be S sub 1, and this small surface element will be S sub 3. Now, for each of these surface elements, we can apply the results that we have there because we only have one point of intersection over these three surfaces. So you can try to generalize the result that we obtained, for example, in here. And we can write the following. So EI of S, of the surface S, so I'm putting these small straight bars because I want to differentiate this S with the lowercase letter s that we used to label the points on the curve instead of the surface. So it is just a way of avoiding confusion, hopefully. Anyway, here we act with EI on H gamma, and this is still equal to 8 pi beta G. And then here we have a summation over all the points P of intersection. We have H, and in this case I'm putting the superscript P. I'm simply using this superscript to remind ourselves of the fact that we are moving along the curve and we are reaching different points of intersection along the curve, I mean the intersection with the surface S. I'm also putting a subscript, gamma 1, and this gamma 1 represents the curve after the intersection, and then I have tau I, and I have HP gamma 2, and in general here I can also put another factor, delta P, where delta P can only take the values plus or minus 1, depending on the orientation of the curve gamma. So it depends on the orientation because at certain points we might be moving up, and then at other points we might be moving downwards. So it is just a generalization of what we have already derived. Now, to generalize even further, we can consider higher spin representations because so far we have only considered the representation of spin 1/2 because we have used the Pauli matrices sigma I and then the matrices tau I, which are these matrices here. Now, we can obtain higher spin representations, for example, by taking certain tensor products of spinors and of matrices of this kind. In principle, we can represent spin 1/2, we can represent spin 1, spin 3/2, spin 2, and so on. And the generators of the group can be denoted in the following fashion. So I will denote them by Ti. So these are generalizations of this tau I here. And here I'm also putting a superscript J, and this represents spin. So, for example, Ti 1/2 will simply be tau I. The index I, of course, goes from 1 to 3, so it can take only the three values 1, 2, and 3. And these operators here, these generators, satisfy the following conditions. We can impose the following conditions. So, for example, Ti j, Ti j. So in this case, I'm only summing over I. I'm not summing over j. This is just the spin index. So we keep j fixed and we are summing over I. And this is very similar to the condition L squared equal to, in particular, when we act with this L squared on an eigenstate, let's call it V, we get j times j plus 1 V. So we impose the condition that this, in a certain subspace, where we are acting with these operators on eigenstates, we can represent it as j times j plus 1, where j is the spin, the genetic spin, times the identity matrix, or the identity operator in general. These operators satisfy the following commutation relation of angular momenta. T, I, J, T, K, J, commutation is equal to I epsilon I, K, L, T, L, J, like this. And so this is just a generalization of the commutation relation between angular momenta. I have already derived something similar in other videos, other courses, but this is not the point of this video. I'm just going to do some abstract generalizations. Now I'm going to define this Rj operator that depends on the connection gamma and the holonomy H gamma. This will denote, so this operator here will denote the spin J irreducible matrix representation of the holonomy of the connection gamma along the curve lowercase gamma. So it's quite complicated to understand intuitively, but this will be a generalization of H sub gamma. In particular, this Rj and this Tij here will generalize this expression here even further, where we have only one point of intersection. So let's consider this for now without considering multiple points of intersections, but this can also be generalized. And so I'm going to rewrite this expression here with the generalizations that we have just considered so far. We act with EI of S on, and in this case we are not going to act on H gamma, because remember that this H gamma here that we have defined is related to, so we have always considered the spin 1/2 representation, basically, because we have used the polymatrices. In this case here, this is going to act on this Rj, and this depends on capital gamma H sub lowercase gamma, and this is equal to 8 pi beta G, and then instead of this H sub gamma 1, here we have Rj of gamma H sub gamma 1, and then instead of tau I here, we are going to have Tji, and then we still have Rj of capital gamma, and instead of H sub gamma 1, we have H sub gamma 2. So this is an abstract way, an abstract notation that we are using, but it is just a way to introduce some loop quantum gravity without going into the very complicated details. So the mathematical details are complicated in general, of course, that's the case. This kind of introductory notation will also help us define or give a definition of spin networks, spin network states, and states of geometry in loop quantum gravity.